seen an elimination reaction that takes haloalkane. Oh, I know what we could do. Takes a haloalkane and converts it into an alkene. That's what eliminations do. So we're in the general area of eliminations, and we have seen, if I start at haloalkane, I can lose HCl or HBr or HI. Oh, somebody asked me about HF the other day. With writing a note to myself. The question was, why have we never seen any fluorines? I'm going to show you at the end why we never see any fluorines, but maybe not today. For this, we're losing a molecule of HCl. This, therefore, is a dehydrohalogenation. And that's going to make an alkene. And we've already let the cat out of the bag and told you that there are two mechanisms. One's called E1 and one's called E2. And we saw the E1 for that. And the E1 mechanism goes through a carbocation. And because it goes through a carbocation, you go through all the usual stuff that you have to do with carbocations. Make sure that it's a tertiary rather than a secondary. And if you can only make a primary, you got to look somewhere else, because primary carbocations are terrible, they're not stable, and you're barking up the wrong tree. You're looking at the wrong mechanism. So it's going to be a secondary or tertiary. Tertiaries would be the best. Okay. The other thing that we could do is take an alcohol and turn that into an alkene. And here, I'd be losing a molecule of H2O. And this, of course, would be a dehydration. We typically need the H and the Cl in a dehydrohalogenation to be vicinal to each other, and therefore make an alkene. And if you have more than one possible product, make the best one. If there's a hydrogen on this group, make the most substituted alkene you can. Somebody spotted that and turned that into a rule. Whose rule is that? Make the most substituted alkene? Zaitsev's rule. Markovnikov's the other way around. Markovnikov says if you start with an alkene and you add to it, make sure that the carbocation is on the most substituted position. Okay? We're doing this the other way, that says if you're going to start with the haloalkane and make an alkene out of it, make the most substituted alkene. All right, alcohols. We're going to do the same thing. I'm going to have an OH here and an H there, and I'm going to want to take them. So it's probably best that they are vicinal. Don't think we're going to see any examples of any big, blatant rules breaking here. I'm going to do a dehydration. Now, oh, I know what it is, though. I also have to talk about. But this is overdue right here. What I'm about to do. I'll probably spend some time today basically just doing general chemistry. I looked at the syllabus. Has anybody looked at the syllabus recently? You don't look at the syllabus daily? Does the class feel like it's going at a breakneck speed? Not really, right? It's kind of just a conversation. We are ahead. We are ahead of what's on the syllabus by about a week. Which is all right, because the syllabus could be completely fake. And it could be that I've only slated a week for a chapter 11 when we're really going to need more than that time. Okay, so I think we've got time to discuss some of this stuff and work through it. In my E1 scenarios, so what I've written on the board so far is true of all eliminations, whether they be E1 or E2. We haven't seen what the E2 is yet, but just believe me. Yeah, I'm going to do dehydrohalogenation. I'm going to turn a haloalkane into an alkene. I'm going to turn an alcohol into an alkene with the dehydration. But in our E1 scenarios, what's the very first thing that happens in an E1? How many steps are there in an E1? There are 2 steps. Let's call them step 1 and step 2. What happens in step 1 of an E1? The leaving group leaves, yeah. All right, how are we going to recognize a leaving group? It's electronegative. There it is. And what we said was, let's have that leave. Okay, things that I can think of that will facilitate the leaving group leaving. It's big. It's electronegative. The bond to carbon is weak. And, oh, what happens when it leaves? This is a chlorine atom, covalently bonded to a carbon atom in a haloalkane molecule. What becomes of the chlorine after it detaches? That was a very quiet but correct answer. Chloride. Ooh. Taking both of those electrons with it, breaking that bond unevenly. What's it called when the bond breaks unevenly and all of the electrons go to one of the participants in the covalent bond? Who? Heterolysis or heterolytic cleavage. That is an uneven divorce. The only time that we see the even divorce was for radicals. Those 2 atoms no longer want to be intimately related in this bond. When it breaks apart, they share the electrons evenly and make a chlorine radical and another chlorine radical. That is about as uncommon in the chemistry world as an amicable divorce is in the legal system. Right? Doesn't happen a lot. It happens 2 times in the entire book. This is a heterolytic cleavage. Both of those electrons end up on that chlorine, making it a chloride. Oh, I had an uncharged molecule here. I just separated a charge. There was no charge on the left-hand side of my equation. Now there is a negative charge in my equation, which means obviously that there's a positive somewhere else. Where am I going to put the positive? On the carbon. So now you ask yourself, is that carbon a suitable candidate to hold a positive charge? What kind of carbon is that at the center of that molecule? Tertiary. Are tertiary carbocations any good? Yeah. Okay. So things that will be an indicator to me that, hey, my E1 is a good candidate to work is I have a leaving group that I can clearly define a big, weak bond with something that is comfortable accepting the negative charge, and it leaves behind a positive charge that is rational. It's on a secondary or a tertiary carbon. If it's on a primary carbon, no, this isn't the mechanism for you. Wait till the next mechanism in the book, because that's your answer. Okay. Take everything I've just discussed right there and write the first step for the dehydrohalogenation of an alcohol. I just did it for a dehydrohalogenation. Let's do it for a dehydration. What's the name of this molecule? It's called 2. It was the second molecule discovered. So we just called it 2. Chloros are lower in the alphabet than methyls. Okay. 2-chloro-2-methylpropane. Let's use the same backbone. And use 2-methyl-2-propanol as our candidate molecule here. 2-methyl. All right. Off you go. In the first example, our dehydrohalogenation, it would be fair to call the leaving group a chloride. That's a chloride leaving group. What would be the name of the leaving group in the dehydration? So, if I just do this, I have a problem. There's a problem. This is not going to work. And it's not going to work for reasons that haven't been adequately explained to you yet, but you do know the answer to. What do we know about chloride? Anything? Fun fact?
Negative.
Okay. Oh, that's actually incredibly important. Okay, what do we know about hydroxide? Is chloride a base? No. What do bases do? Yeah. Bases make bonds. So what did you just do to my super powerful base? You just broke its bond. How do you think that the base feels about that? Bases have no feelings. No. That's a no. That is a no, 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 no. No, 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 no. No, 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 no. No. Hydroxide is a base. And bases make bonds. And yes, this reaction works, otherwise I wouldn't have put it up on the board. But it doesn't work this way. You cannot just have something that is powerful at making bonds fall off your molecule. That's not how it works. This makes bonds. It's a base. Bases make bonds. They are electron pair donors. It's going to make that bond back in the blink of an eye. So our equilibrium lives so far to the left that this does not happen. So, not everything that's electronegative is automatically a leaving group. We have to look at how that works. Good leaving groups have the following characteristics. They're electronegative. They have to be. They have to be electronegative because they have to be part of a bond that is uneven. They have to be part of a polar bond because that bond has to be weak. And polar bonds don't have the electrons slap bang in the middle. I know that's kind of a Gen Chem approximation of what electrons are doing in that bond, but they don't. Hey, it also helps if they are large, because here's my carbon. If, in order to make the leaving group leave, who's carbon? Okay, let's just pretend for a second. Here's a fluorine. Is fluorine bigger or smaller than carbon? Look on the periodic table. Yeah. Bigger or smaller than carbon? Smaller than carbon because it's in the same period and to the right, and as you move across the period, the atoms contract. Remember effective nuclear charge? Who did you all have for general chemistry? I know it wasn't me. Who did you have for general chemistry? Okay. Did she teach you effective nuclear charge? That's the Z effective thing? No? It's a very small section of the book, and there's nothing more important in general chemistry than effective nuclear charge. It describes everything that you need to know. Putting more protons at the center of the nucleus makes it progressively more and more positive. So the electrons that are floating around that positive charge get pulled in towards a progressively more positive nucleus. So as you move carbon, nitrogen, oxygen, fluorine, these atoms get progressively smaller. It's counterintuitive because you're putting more stuff into the atom and yet they're getting smaller. All the protons have to be in the same place. The electrons shrink in to meet that attraction. It's called a contraction. That's the moving left to right across the periodic table. The atom sizes get smaller. So if I have to remove this fluoro, hey, it's electronegative, but it's not big. If I have to move it to here to completely snap that bond, don't need to be that far away. To completely snap that bond, I need to move the fluorine to here. Okay? Here's a carbon. There's a bromine. Can you see how much easier this is going to be to break? Because the nucleus to nucleus distance here versus here. It's already down the path. Easy to break. So if the atoms are big and electronegative, fluorine is not a good leaving group. Big and electronegative, hey, I've got an advantage. And then they cannot be bases. They cannot be bases. So, everything you know about bases, go. They're electron pair donors. How do I recognize by looking on the periodic table if something is a base? All right, is calcium a base? Is silicon a base? Is sulfur a base? Yeah, we don't know. You do know, you just don't know that you know it. It's called, what is that? A known known is something that you know, and then a known unknown is something that you know that you don't know, and then this is all Donald Rumsfeld. I guess this is an unknown known. This is something that you know, but it's never been pointed out to you. Because in general chemistry, count the number of times that we mentioned bases in general chemistry. Like one hand. It was all acid, 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 acid in general chemistry. Well, guess what does all the bonding? Bases do all of the bonding. We shouldn't have been telling you all of that stuff about acids. Why did we not talk about bases in general chemistry? Economics. There's only one base, and it's the cheapest one, and it's the best one. Sodium hydroxide is the cheapest base, and it is the best base. It becomes a monopoly, and at that point we don't need to talk about it. It's as if, think of something in your life where you have a choice as a consumer, and the best option is also the cheapest. It doesn't happen. It doesn't happen often. Sodium hydroxide is one of those cases, and so we don't talk about anything else. Need to be a weak base, and sadly we don't know what bases are because we spent all our time talking about acids. But if we remember what acids are, bases are the opposite of acids. Acids are electron pair acceptors, bases are electron pair donors. So if I can remember from general chemistry what the trend in acidity is, then I automatically know what the trend in basicity is, and I can solve my underlying problem here of choosing the right molecules to do eliminations with, because this is not the correct candidate. Currently, I'm going to make it be. I'm going to turn this from being something that cannot be eliminated, because that is too strong of a base, into something that will give away the alcohol group. No problem at all. So, let's go back and look at the periodic table and revisit the periodic trend that describes acidity. There are two trends. One is horizontal and one is vertical. Let's do the vertical one first. So I'm going to have some space. Right here I'm going to go fluorine, chlorine, bromine, iodine. It should be iodine. Fluorine, chlorine, bromine, iodine, astatine. It's not iodine. Okay. Okay, I'm going to talk about acidity. So the thing to do when you talk about acidity add hydrogen and make each of those atoms actually be the acid. All right. What do we know about HCl?
It's a strong acid.
Okay, what does that mean? To be a strong acid, what does being a strong acid mean?
Completely associates in water.
Completely dissociates 100% in aqueous solution. That would be a definition of a strong electrolyte, in this case, strong acid. What do I know about HBr? Same thing. What do I know about HI?
Same thing.
Same thing. What do I know about HF?
Weak acid.
HF's a weak acid. It dissociates, but much less than 100%. So what is the trend in acidity down group 7? Which one of the atoms in group 7 is the most acidic? That's the most acidic. Which one's the least acidic?
Water.
That's the least acidic. So acidity goes this way. What is the reason that acidity increases down the group? Size. There's an H and there's an F. Here's an H and there's a Cl. Here's an H and there's a Br. And then here's an H and there's an iodine. size, not electronegativity, size is the determining factor of that acidity trend. Okay, so this is, we have names for this. We call these the free acids. That's the free acid. When it splits apart, what was the H plus part called? It's the conjugate acid. And what is the F minus part called? That was the conjugate base. Okay, so if the acidity trend for my free acids down the group goes from top to bottom increasing, what is the basicity trend of the fluoride, chloride, bromide, and iodide? If acidity increases from top to bottom, which way does basicity increase? Has to be the opposite way. Okay, which means iodide is actually too good of a leaving group for us to use. That's why you don't see an awful lot of iodo compounds around. Bromine's fabulous leaving group. Fabulous leaving group. They tend to be a bit more expensive than chloros. And so if you can do the same reaction with the bromo and a chloro about equally, we use the chloros just for economic reasons. And fluoros, oh, that's now too basic to be a good leaving group. This is a good leaving group. LG leaving group. This is a good leaving group. But that one right there, that is too electronegative, too small, too much of a base. That is a poor leaving group. If it's a weak base, how interested is chloride in getting back with the H plus to make HCl? In solution, how here's a bottle. It's filled up to the 1 liter mark. And the label says that it's 1 liter of 1 molar HCl. How much HCl is inside the bottle? How many HCls are floating around inside the bottle? None. We just told you, it separates. We used the term 100%. There is no HCl in that bottle. None. There is H plus and there is Cl minus. 100% dissociated. That was our definition from GenChem. So how interested is that chloride in us reassociating with this H plus and reforming the HCl? Not at all. So does that make this chloride a base? Not at all. This chloride has no interest in making new bonds back to the H plus. Makes it a weak base. The conjugate base of a weak acid is weak. But fluoride does not come from a strong acid, and therefore this is not a weak base. Therefore, we don't use it as a leaving group. Okay, trend discovered. Moving on. That's the vertical trend. What about the horizontal trend? Here we go. Carbon, nitrogen, oxygen, fluorine. I'm going to do the same thing. I took the individual atoms and then I added hydrogen to them to make the molecule that would determine what the acidity trend was. I'm going to do that again on my horizontal scale. So starting with HF, I took the F and I added H to it. F is in group 7, so it only makes one covalent bond, so I only needed one hydrogen. Oxygen is in group 6, so it makes 2 covalent bonds, so it needs 2 hydrogens. Nitrogen is in group 5, so it makes 3 covalent bonds, it needs 3 hydrogens. Carbon is in group 4, it makes 4 covalent bonds, therefore I'm going to need 4 hydrogens. Okay. HF, if it were an acid, would split apart and make H plus and F minus. H2O, if it were an acid, would split apart and make H plus and hydroxide. Ammonia, if it were an acid, would split apart and make H plus and NH2 minus, called amide. And CH4, methane, if it were an acid, would split apart and make a methyl carbanion. Okay, I can know the basicities of these materials right here. And I can know the trend, although no one's ever pointed this out to me before. I can know that trend if I know what the trend in acidity of the top blue molecules is. And maybe I know that. This molecule is called methane. This molecule is called ammonia. This molecule is called water. And this molecule is called hydrofluoric acid. Which one of those molecules is the most acidic? No? Not immediately obvious? Let me just say that again. Methane, ammonia, water, hydrofluoric acid. If it has the word acid in its name, there's more than a passing chance that it's acidic. So my acidity trend goes that way. That means that the basicity trend for these anions, fluoride, hydroxide, amide, and carbanion. We've seen carbocation. This is its opposite. This is a negatively charged basicity. Goes that way. So, there's no way possible that I can remove a hydroxide with a fluoride, because this is a stronger base. There's no way possible that I can remove a carbon to nitrogen bond with a carbon to oxygen bond. And I can't remove a carbon-carbon bond with anything. And in fact, if we look, the number of times that the carbon-carbon bonds break in the book happens maybe 2 or 3 times in the entire book. Carbon-carbon bonds don't break because the carbons are just far too basic. Just too basic. It's not going to happen. Okay, so this now, hydroxide is too strong of a base. I am not going to be able to dehydrate hydroxide unless I try really hard. Okay, let's go back and visit our reaction. Does that all make sense? Quite simple logic. We didn't know anything about bases. Bases make the bonds, so we have to pay attention to them. They're just the opposite trend of acidity. So not that difficult. Here's my E1, dehydration of an alcohol. This is a nice, simple molecule to work with. There you go. There's our 2-methyl-2-propanol again. Okay. The alcohol itself is too basic to be a leaving group. Because my leaving group, if I had it leave, would be hydroxide, and hydroxide is a powerful base. And having been told that the problem with hydroxide is that it's a base, that therefore is what tells me the answer. So instead of trying to pry this thing off the molecule with a hammer, why don't I just invite it to leave in a different form? If this is a base, why don't I let it be a base? Here's acid, has no electrons. Here's the base, has a pair of electrons. Motion of 2 electrons is a curved arrow. Low pair of electrons on the oxygen reaches out and grabs a small amount of acid. Which acid should I use? Don't use HCl. Go ahead and use a tiny amount of sulfuric acid. What's wrong with my sketch? Uncharged molecule, positive charge. Positive charge is missing.
Oxygen has 3 bonds.
Yeah, oxygen is in group 6. It needs 2 bonds in order to make an uncharged molecule. If it has 3, then you've done something not wrong, but you have to explain yourself away. That's positive charge right there. 2 bonds on an oxygen, no charge. 1 bond on an oxygen, negative charge. 3 bonds on an oxygen, positive charge. 2 bonds, no charge. 1 bond, negative charge. 3 bonds, positive charge. Got it? Okay. That oxygen is still electronegative. That bond is still weak. Only now, what's my leaving group? Water is the leaving group, not hydroxide. Hydroxide was too powerful of a base to leave this molecule. I just turned it into water. Water is 70% of the planet's surface. Here's just a simple rule of thumb. If you are sketching something out and the reaction that you have sketched out on paper has water as a product, it probably works. Water is an insanely stable molecule. That's why there's so much of it. Let's have it leave. Okay. Carbocation. All of those methyls are equivalent. I put a positive charge, conveniently on the most substituted carbon. And now I have to sacrifice the electrons that are in that carbon-hydrogen bond right there. All the hydrogens are the same. All 9 hydrogens in this molecule are the same as each other. They're all the same. Lone pair of electrons right here will pick up that hydrogen as an H+. It will donate its electrons in. I made my alkene. And I got my acid back. So the acid goes in at the first step and comes out in the last step. What is it being? What is it doing? What word can we use to describe it? The reaction does not occur without the acid. The acid is not consumed in this reaction. Therefore, it is a catalyst. The acid makes this reaction occur. Without the acid, this reaction does not occur. It is consumed in the first step and then pushed back out. So it is not consumed in the overall reaction. But the reaction does not occur without it, therefore it is catalytic. Okay? That's how your dehydrations work. You just put them, when things are not working for you because they're too basic, you put them in acid and you let nature take its course. The other thing to note while I'm still talking is because we do not have a negative charge anywhere in this mechanism. If you perform a reaction in acid, you will not have negative charges in that mechanism. Because a negative charge in the presence of acid is immediately going to get engulfed. So there's no negative here. And without a negative, those reactions do not push forward. They're all ambivalent. They're all, I'll do this. They're all equilibrium. So in acid, we're going to get used to having equilibrium arrows and no negative charges. Okay. I was looking through my computer this morning. I think I'm going to put together a practice test for you and post it hopefully today. I think I can do it today. I'll do it. I will do it today. There you go. That's now a promise. And then you've got that all of next week, to, whole weekend, and then all of next week to look at. Okay. See that?
When is it?
Friday.